Okay, so we're starting now. We're having a look at turning points. So just as a quick refresh, whatever, okay. Quick refresh question I want you to do for me. I want you to find this point here, the vertex, using complete the square. Okay, so this is a quick refresh question. Should only take you half a minute. Give me the vertex here. I want both the x and the y. Yeah? So completing the square gives you x minus 2 squared, yeah, plus 6. So this is 2 and this is 6, and the point 26 is called the vertex. Another name for vertex is turning point, because if you look at the graph, it's where the graph turns. To the left, it's heading down, and on the right, it's heading up. So this is a point where it sort of turns, like it does a U-turn. Okay. So there are many, many names for this point. Earlier we learned one name, we called it a vertex, right? But we also have turning point. Does anyone know any other name for it? Yep. A min or max point. Good. What else? Any other?
Extreme.
Yes. Extreme point. Where did you find that word? Yeah. Okay. Maybe without looking. Any other words? So we have extreme. Well. Critical. Yeah.
Stationary.
Yeah. All right. Fine. Stationary. Stationary point. Optimum's a good one. Yeah. Optimum. Yeah. I can't really think of any more, but you get the idea. They all mean the same thing here. Okay? The problem is we don't always have a quadratic. So this method of completing the square only works for quadratics. Alex. So we need a method that works for any graph. Okay. Now what's interesting about the vertex is that if you were to draw the tangent line here, what's the slope of it? 0. So all these points, well, they're the same thing, all these points can be found by looking for where the slope of the tangent will be 0. Now, to prove that this works, let's take this example. So what is dy dx here? 2x minus 4. And I need to know, where is this going to be 0? Derivative of this. Yeah? This is what we did in the last lesson. So I get 2x equals 4, so x equals 2. Which is not a surprise because it matches up with this. Although, with this method I don't know the y, unless I do what? Yeah, unless I sub it back in. Then I get y equals 2 squared minus 4 times 2 plus 10. Yeah, which works out to be 6. But what's great about this method is it works for any problem, not just a quadratic. So, in a moment, we'll do an example involving a cubic. But I'll just let you write this down. Some people knew about this method already when we were doing the lesson on completing the square. Okay, so we're looking at it now. Okay, write this down, please. Are you sitting there to be nearest to the heater?
No.
Oh, okay. So I was wondering if I start to see the class distribute along the wall as time goes on. Alright, have we got this? Yeah. So, have we got this? Yes? Okay. So, let's have a look at a cubic example now. Let me do something. Y equals 2x cubed plus 18x squared plus 54x minus 24. No. Well, it'll do as the first example. This is a good example to show you a slight... Well, no, I won't say anything just yet. Okay, so let's get the derivative. So let me see, what would be that now? 2 times 3, so 6x squared plus 36x plus 54, and we want to make this 0. I believe I can divide by 6, can't I? That'll be x squared plus 6x plus 9. And this gives me x minus 3 times x minus 3 equals 0. So x equals 3. Can somebody give me the y value by subbing it back in? Huh? What did I do wrong? Oh, sorry. Plus, plus, and minus here. Thank you. So, if we sub this back in... Oh, thank you. What you get, Ray? Minus 78? Yeah. Minus 78. Now, just a second here. What I'd like to do is just graph this. Okay. Yeah. We get one. Patience, little one. We'll get there, okay? Do you understand what's happened here because there's only one answer? Exactly, so one unknown at a time. Right, did you write that down?
No,
Yeah. What part are you at? Okay. So, I'm going to make the graph. What do we think this point will be? A minimum or a maximum? Oh, good. Yeah, yeah. Or both. Oh, interesting. I prefer his answer. Yeah. What do you call this? Oh, there's a name for it. It's not. Well, okay. Let's see. What was it? Y. 2x cubed. We'll see now. 2x cubed. Yeah. Yeah. All right. Now I'll have to zoom out, obviously. Goodness, hang on, let me adjust the scale here. So we're at minus 3, aren't we? Minus 3, minus 78, which actually looks pretty decent. That's that point there. Is it a maximum? No. Is it a minimum? No. So what's interesting about this method when you look at something which isn't a quadratic, because only quadratics are guaranteed to have a maximum or a minimum. We haven't found a maximum or minimum. Does anyone know what this point is that we found? Yeah, but special type. Yeah, I'm not using one of the words from earlier. It's a different... an in-between point. Anyone know it? No? No? Saddle point. Saddle point. Yeah. The saddle point, like a horse saddle. You know this word, saddle? Yeah. Yeah. Now, can you all picture a horse saddle? Yeah. Depending on the way you sit, depending on your point of view, you can either say you're at a minimum or a maximum. So from your side, you're kind of sitting on the top of a hill, aren't you? Yep. So you would say you're at the maximum. However, frontwards, you know it curves up in the front for where you put the reins. So you could say you're sitting at a minimum. You know, similar thing is happening here. If you were moving down this hill and you got to here, you would conclude you're at a minimum. But if you were climbing this hill and got to here, you would conclude you're at a maximum. So it's a saddle point. It's not maximum nor minimum. But why did we find this point? Well, look at the slope. Would you say this is flat here? It is. That's why we found it, because it is flat there. Okay. So this is an example of a saddle point. This is an example of a saddle point. Is this a new word, or when people thought they knew this word before, is it? Or was it a different word? Was it a different word? Can't think of another word for it though. Can't think of another word. Anyways, can I scroll down? Yep. So, let me give you a cubic to try and then I'll do it. Y equals 2x cubed minus 3x squared minus 36x plus 30. I want the x and the y turning points. The only other word I could think of, but it's not the right word, is, were you thinking of inflection? No? Inflection? No, okay. Yeah, you got it? No, because you'll be guaranteed to get 0 if you do that. You put it into the original. Because you're looking for the y, not dy dx. Yeah? Got answers? Two answers? One answer? Two answers?
3 minus 51 and minus 2, 78.
Let's have a look. What did you get for dy dx here?
6x
Yep.
minus
Good. And obviously we can divide by 6. So minus 3 plus 2. So that means the first one is minus 2, and then 3 is the second x value. By subbing these x's in, we can get the y's. What did you say you got for minus 2? 74. And for the 3? Minus 51. So what's happening here is you actually do get a max and a min. This is minus 2, 74 would be like up here, and then 3 minus 51 would be down here. And what has happened is the graph gets a max turning point here, and then a min turning point here. That's why you got 2 answers, because there were two solutions. There was a maximum turning point, and then there was a minimum turning point. Now, a little bit of vocabulary here. Question? Yeah. No, I'm just drawing to help explain the answer. This maximum point here, and say this maximum point here on a quadratic, there's something a little bit different about these two. I mean, they're both maximums, but they're not quite the same type of maximum. Can anyone see a difference between the cubic maximum and the quadratic maximum?
For example, in quadratic, there is no another point that can be higher than.
That's it, yeah. On the cubic one?
We can have a plus infinity.
Yes, that's it. You can go to plus infinity. So the big difference here is this maximum is a maximum everywhere. There is no other point on this graph that goes above it. Right? It's not like the quadratic goes back up. But this maximum, well, it's not quite the maximum the way you might think it is, because if you go enough to the right, eventually you'll get higher than this maximum. So we distinguish this by saying it's only a local maximum. It's only a maximum in its neighborhood. Whereas this guy, absolute, or what's another word, the opposite of local? International. Thank you for that contribution. No, not international. Maybe a more mathematical word. No. Global maximum. Global maximum. This one is. Global maximum. And likewise, how would you describe this point? A local minimum. Yeah. Okay. Right. Can I scroll down? Yep. Right. Okay. I'll give you a hard one to try now. Y equals log of x power 16 minus x squared minus 14x minus 3. Get me the turning points. Alex. What? No, it's too early in the question to be using the calculator.
Teacher, minus x squared. Is it squared?
Yes. Sure. this your calculator you had for the exam? Okay. Now, are we getting answers up here? Oh, I see lots of thinking. Do we have answers? Perhaps. All right. You look like you're thinking deeply about this. Do you have an answer?
Yeah, if you put 1 over this and then you put it in brackets to the power minus 1.
What did you do about the 16? No. No. Yes, yes, yes. It is, yeah. Right. Let's have a look. So, the first thing you were supposed to do before you even differentiate is to bring the 16 down in front of the log using your rules of logs. Only now can you differentiate. Yeah, that's it. 16 over x minus 2x minus 14, yeah, equals 0. Now, what's to be done next about this? Good, yeah, so you'll get 16 minus 2x squared minus 14x. I'll bring everything to the right. Did I do that right? 2 plus plus minus, yeah. And now, divide by 2. So, let's see. 8 and 1? No? Yes?
Yeah.
Again.
I just factorised there.
Oh,
1 or minus 8. So if 1 is easy because that's 0 minus 18. Although I won't be able to do this one. You might, what is it? 95? No, not undefined, no. 78.27. Now you have to be careful with how you type it in on the calculator because you're typing in log bracket minus 8 bracket 16 bracket minus 8 squared minus 14 bracket minus 8 minus 3. Just be careful. More brackets is better than not enough brackets.
Why is negative 18? 1 negative 18.
When you put 1 in, I believe it'll come out to be minus 18. If you sub 1 in for x, you should get out minus 18. And then if you sub in minus 8, you get out 78.3. Roughly, yeah, it's a decimal. Yeah? Why did you say it was undefined? I know your reason, but tell me. Correct, you can't have log of a negative. But why is that not a problem here?
I don't know.
Good.
Because the power is an even number.
Exactly, because the power is an even number.
So it becomes positive.
Exactly. So the log is never actually taking a negative value because the power first hits the x before the log hits it. So the power 16 protects the log from minus values. I want to have a look at this graph now. So when you're ready, I'll graph it. You think you have a picture of the graph? You know, maybe it'll look like the cubic because we have 2 points, you know, a max and a min. Maybe not. Let's have a look. Yeah?
What was the answer for the last?
For which step? Everything's on the screen.
No, the last one.
What do you mean?
This one. No,
Huh?
the upper one.
78.3.
Ah, okay.
Can I go to the graph?
Yeah.
Yeah. So let's have a look at what this looks like. What was it? Y equals log x power 16. Next.
Minus
Minus
x
x
squared
squared
minus 13x minus 3.
Like that? Okay. Now, actually, let me reset this. Okay. No, I need to. There we go. Whoa. What were our two values for x? 1 and minus 8. So I need to have minus 8 on the screen. Whoa. And then. Yeah, let me a little bit more. Oh, good. That's better. So, okay, I think we can all agree that at, what was it, minus 8 and 70 something. We can all agree that we have found the maximum point here. And is it a local or a global maximum? The global maximum. And what was our second point? It was 1 and... Which is this one? Which is... What type of point? Local what? Local maximum. Now, this is an interesting example because you might have thought if you have 2 points, one should be max and one should be min. Whereas this example, interestingly, both are max. It's just one of them is a global max and the other one is a local max. Does it look like we maybe have missed a point? Yeah. Where? Here, yeah? What would you describe this point as? Local minimum. Let's zoom in and see what we have going on here. Where is that center on cross button? Center on cross? No, that's center. Ah, that's in a later lesson. We'll get to that. Center. Oh, good. Okay, now where's zoom in? Zoom out. Zoom in. Right. So this looks like 0 and minus. What would you say? Yeah. Let's zoom in a bit more. What do you say now? Okay, hang on. Hold on. Let's see. Okay. Oh, yeah. So, what's happening every time we try to get closer to it?
Oh, it's minus.
It's minus infinity. Just the graph makes it look like it's reaching a point, but in fact what's happening is it's shooting down to minus infinity. So it's not a turning point, because you actually don't have a point. It just shoots straight down to minus infinity. Okay? And anyways, even if it was a turning point, even if it did reach a point, we're forbidden from using it. Why? No, it is 0. And besides, we're allowed to use less than 0, remember? Why can we not use it even if it was a turning point?
It would be minus infinity anyway.
Yeah, but just the x value. Like, why can't I say we have a turning point at x is 0? I suppose it didn't go to minus infinity. Well, we're not allowed to use it because This is only defined for all x except for 0. You see, remember you said earlier, oh, we can't use negative, but that's okay because it's an even power. But we can't use 0. And the power 16 does nothing about the 0. It keeps it as 0. So we couldn't use an answer that had x is 0 anyways. Because remember when we did the lesson about what values of log we can use? We can't take the log of 0. This is not allowed. So we knew from the beginning that whatever answers could be, they could not be 0. Okay? Now that's a harder example. In the exam, they sometimes give you a log one, but my experience is 90% of the time it's a cubic. And as Matar was asking me, how can we know, without drawing the graph maybe, if it's a max or a min? And that'll be in a later lesson. We have to use something called the second derivative. Okay? You've heard of this one. Yeah, okay. So what I want you to try now for a few minutes, let's see. I'll give you, let's say, question 1, question 2, question 3. And then question 26 is just a quadratic. So there's 1, 2, 3, 4 questions to do for the next about 5-10 minutes. Wait, just give me 1 second to get some energy back into me. No, just 1 second. I know it looks like I have infinite energy, but I don't. I really don't. Let me save.